Hi, this is Clay Hearn with Applied GAX. I'm here today to give you a quick run-through demonstration of STAR-CCM Plus, focusing on the workflow. So what we're going to do this morning is quickly bring in a 3D model and show that how we can use the meshing pipeline within STAR-CCM Plus to extract the fluid volume of that part that we're interested in. And then we'll go ahead and apply the physics, define boundary conditions, and mesh our fluid volume. We'll be able to set up a few post-processing images and post-processing data and be able to run the model, evaluate some of the results that we get from the model, and also look at ways that we can improve the results that we get, again, by going back into the meshing pipeline that is offered within STAR-CCM Plus. I will quickly switch over now to the program, and this is what you first get when you open STAR-CCM Plus here. We will just quickly kind of introduce you to the user interface. Up here you've got what is the toolbar and taskbar that you have in pretty much every program out there. On the left panel we have what we call the navigator plane here. Down here will be a properties plane, and our output box is down here. The output box will provide feedback to the user on various information that is performing when you're either meshing or you're running a model. And the big box that we have here is our main toolbar. So first we'll start off by creating a new model. So here you've got, in the navigator plane on the far left window, we've got some of the structure that the engineer and the user will use to organize the model as they build the model. And we can see down here there's also a properties box that showed up. And this property box will kind of provide feedback to the user about specific items nested within this navigator explorer pane. First thing that we need to do is we need to bring in some of our geometry. So we'll go to File, Import Surface Mesh. And we're going to bring in a manifold right here. So we see this is the manifold piece. And typically, as a CFD analyst, this is what you end up getting much of the time to start your analysis. Most of the world works within kind of the actual component, the actual part itself. As a CFD analyst, you are really focused on what's inside the part. We're not really focused on the actual manifold itself. It's nice. It's got some flanges for bolting on the side, but we're really focused on whatever fluid or air or gas is moving through this. So one of the first things that we're going to have to is extract that volume. If we explode out the geometry panel here, we can see the parts that we brought in, and it's labeled as the manifold right here. If we extrapolate this, we see that we've split this up into faces, and we're defining this right now as kind of an inlet face is separated here. And then we've got an outlet face here where we have 4 ports. So we'd like to do a simple study where we bring in fluid through the inlet face and see how it gets divided up into the 4 outlet ports. So to extract the volume, the first thing we're going to do is cap off all these edges. We're going to start building up what's called a meshing pipeline through a series of operations in the geometry. So the first thing we want to do is cap off those holes, and we'll use the command fill holes, where we go select our manifold part as the input part, and then we're going to select our inlet and outlet faces. We're also going to select some curves that kind of separate the 4 outlet ports that we have here. And we execute this upon creation, and we see we now have surfaces that were created within STAR-CCM that block out all these holes. So we've blocked out the main 1 inlet port and the 4 outlet ports. We also see we've blocked out all the little bolt holes. For now, we're not really going to be too concerned about that, because in the next operation, we're going to extract the volume. And it's going to be smart enough to figure out, what surfaces are associated with the exact volume itself. So for the, again, operations extract volume, we're going to hit fill holes in the manifold, execute beyond operation, and we now have an actual volume part that's been created that's shown here as extract volume. And we can rename this to give it something a little bit, more useful, such as fluid volume. And we can drag this into the geometry scene that's been created so that we can see it in our scene. So the next step is, once we've defined our volumes, we got to define it to a region, and the region is going to be what's used within STAR-CCM to identify some aspect for the analysis. There's going to be a fluid body, or regions could represent fluid or gas bodies, or moving, separate areas that are moving, or possibly also solid bodies used for heat transfer. And we'll assign that one fluid region as its own separate region. And we see here we now have the fluid volume defined as a region, and we've got the surfaces defined, where the faces are the walls on the pipe. And then we've got our inlet port and our 4 outlet ports. We want this to be a velocity inlet, and we want the 4 outlet ports just to be standard outlet pressure ports. Now, there's no other options showing up here because we don't have any physics. So the next thing we have to do is define what the physics are going to be. So we go to Continuum, Continua, New, Physics Continuum, and we can select our models. And the power where STAR comes in is it's a multi-physics analysis tool. The amount of physics options that you have in here are quite frankly, a little bit overwhelming. But for this analysis, we're going to kind of focus on just something very simple. We just want to have this as being liquid, being water, going through the pipe. It's a steady state analysis. So we're going to select our space. It's 3-dimensional space. It's going to be a steady state analysis. We're going to do liquid, a segregated flow, constant density. And we're going to assume there's turbulence in it, and use the K epsilon turbulence as our primary model. As you can see, I've selected maybe actually 4 or 5 different models. There's a lot of submodels that automatically get selected, kind of based on that to speed up the time. Now that we've got our physics selected, we can kind of go back here and actually have some options on what to do with this. So for velocity magnitude, we can increase this to about 2 meters per second. And then for the outlet pressures, right now we're just going to keep that the standard 0 pascals. That's based off of the reference pressure. So the next thing that we would have to do is to mesh this region. We've now got our boundary conditions applied. It is important to apply the boundary conditions before meshing because it helps guide the meshing structure. And we will see that in a little bit. So the mesh, we go to New, Mesh, Automated Mesh. And we're going to select our fluid volume as the part we want to mesh. First thing we want to do is the surface remesher. And this is essentially going to come in. It's a very important step, but it's going to come in and just remesh the base surface of the part we have. We're going to use a polyhedral mesher. The polyhedral mesher is actually one of the main developments in STAR-CCM Plus. It creates cells that are multifaceted, 16, 20 sides, polygons. And the benefit of these cells is that you make sure that you have a surface that's perpendicular to a flow. So you get more accurate analysis results. It's especially useful for areas where you're going to end up having swirling flow. And the last thing we want to add is a prism layer. And the prism layer is going to create thin, wafer-shaped cells right near the walls of our part, and this helps better resolve the boundary interface between the fluid and the wall interaction. We bring in the automated mesh into our operations. And if we expand this out, we can see the options that we have for meshing that are available. Right now, we've got a base size. Base size always comes in as 1 meter. If we look at some of the other options, we've got, a target surface size, a minimum surface size, and we can see there's a relation that we can set these as a percentage of the base size. This means that you could select your minimum surface size, your prism layer thickness, all and other custom controls, all as a function of the base size, so that you would have one number to change if you were doing a mesh sensitivity study that would update everything else with respect to one number. So one thing that's always a good question is, what to set your base size to. And it's, usually a good idea to pick some feature of the geometry that you have in question. So if we were to grab our measurement tool up here and try to measure, say, the width of this channel, we see we got something that's about, 45 millimeters across. So we could set this base size to maybe half that, or about 20 millimeters across. We'll make some additional changes to this. We can increase our minimum surface size to about 20% of that. And we'll also change some of the aspects of our layers. Increase the number of prism layers up to 4. And decrease the prism layer thickness to about 20%. And the next thing we can do is we can right-click Execute to mesh this region, or we can hit one button up here that will perform the meshing for us. As it's meshing, we see now in our output window, it's kind of come alive. It's providing us feedback on the status of the meshing operations. We see we've got about 36,000 cells that have been created. If we want to view the mesh itself, we can create a new mesh scene right here. And this is our new mesh scene of the entire region that's been meshed. And you can see the shape of the polyhedras that have been created. Almost makes it look like a snake skin that's been put over. We can see the end faces here, the end of the prism layer cells on the inlet and the outlet ends. And that's what predefining the boundary conditions actually does for you. It tells the mesher not to put polyhedral cells there. If we want to get a good view of what it looks like through the midplane, we'd also like to, get some views of the flow through the midplane too. Get some flows through the midplane too. We can create a derived part, new part section, a plane. We'll make this perpendicular in the y direction, so it's straight up through the middle of the part. We can add this to our scene. Right here. Hide the rest of the mesh. And we see we have the midplane of what the mesh looks like as you cut through the part. And we can line up right here. And we can take this view and we can store this view for future reference. Because the next thing we'd like to do is we'd like to see what the velocities look like as it flows through this part and primarily through this plane. So we'll create a new vector scene up here. And we'll reorient to the view that we just had created. In the vector scene, we want to grab that cut plane that we defined again. And we're actually going to not do traditional vector where you have arrows. We're going to do what's a line integrated convolution, where it basically takes the path and creates lines that show, more the direction and the tangency of the flow. It's a little bit better, in my opinion, for kind of showing how the flow is swirling throughout the manifold as it passes through. A couple other items that we'd like to come up with is developing some reports that can progress certain engineering aspects So it'd be interesting, what's the overall pressure drop through this manifold, and how is the flow actually splitting through these 4 outlets. So we can do that with a report. So the first report we're going to create is going to be a pressure drop report. We go to our pressure drop and we select a high pressure, which is going to be the inlet. And we'll select one of the low pressures, and this could be outlet 4, which should be this outlet way over here. We'd also like to create 4 more reports that are going to be the outlet flows for each of the 4 outlets. We'll do that as mass flow 1. We'll do that right here as mass flow report 2, relevant to outlet port 2. Mass flow report 3 for outlet port 3. And mass flow report 4 for outlet port 4. So now that we have these 4 or 5 reports, we want to create some monitors and some plots for them so that we can see how they're converging during the analysis. So we can right click here, hit create monitor and plot for report, and it automatically creates a report for pressure drop. And then we can select all 4 of the mass flow reports to create and plot monitor from report for this and put it all in a single plot. So now we have our scene image and our reports. We can hit the run button here and perform our analysis. We see the analysis starts applying the residuals, which is kind of a key metric to use when you're trying to judge convergence. We want these residuals to go down a few orders of magnitude and at least get to a part where they're going to level off. We can go to our scenes plot over here and see how the flow is developing through our midplane. We can see how the pressure drop is being calculated. It looks like it's pretty much getting to the part where everything's leveling out. And we can say this is probably a pretty good converged result that we have here. We're not going to get any more improvements by running it further iterations. If we look over at our vector scenes, we see something kind of curious that's occurring right here. We see lots of swirling at the first 3 outlet ports. And, this swirling isn't really a good indication when you're having it cut through an actual boundary, because we've actually put static boundary conditions on each of these 4 ports, forcing a pressure condition at each of these 4 ports. And we see, you've actually got these warning messages that are popping up saying you're having reverse flow on these outlet port faces. And typically good in practice and analysis practice in CFDs to make sure that your boundaries that you're applying are situated some nominal distance off the part that you are actually have an interest. So typically you don't want to be forcing boundaries like this, and it's pretty easy way to make a correction here in STAR-CCM Plus so that we can address this concern by extending these boundaries out. And what we're going to do is we're going to create kind of a surface extended features. So we can go here to new surface extruder, and we'll select our main part that we're concerned about, the fluid volume, and we select the 4, 5 input surfaces, because we'd like to do this on all the surfaces that we have. And we'll extrude it out about 0.25, and that's about 5 times the width, and create volume and meshing options from that. And we create a new part here as it's extruded all these faces, so we will now have well-developed flows on the inlet and outlet. As we're solving, that's our region of interest. We do need to assign this to a region, and we'll assign this to a separate region. And we have our region right here. Now, one thing to kind of bring up in mind is if we look at our original region where we had these boundary conditions defined before, they're now kind of masked over by interface constraint. We actually have to assign our boundaries at the new extensions that we created. We do have to reset this boundary and make it I think it was 2 meters per second that we had before, and then these 4 just become our outlet pressure conditions. We need to execute this last volume extrusion, and if we can see, going back to the mesh and back to the original mesh that we had, when we add the new parts that we meshed to it, we've essentially just taken that parts that we had and extruded it out. One thing that did forget to do is we have a default of a number of parts. We'd probably a number of cells that's extruding. We'd probably like to improve that a little bit. So we can go back to the volume extruder and increase that number of layers to 30. And again, we just have to rerun that one part. And we see we got a quick update here. Now, the last thing we need to do to run this is, because like I said before, we had overwritten this previous surfaces that we had been using for calculating our pressure drops and mass flows. We need to update those real quickly. So that's quickly just going in here and updating to the new boundaries, interface boundaries that have been defined with those contacts. And this is one of those areas that it's a little bit tedious here for this demonstration. If this was something that you did quite a few times, or you knew to make these extrusions in the beginning, you wouldn't have to do this again. But you could also create macros that would kind of automate this process for you. But once we've made these corrections, we can go through and rerun the analysis and basically just pick up exactly where we left off on our results. And we're going to kind of real quickly take these and kind of lock down what we have. Or we're just going to run this as is. And there's going to be a lot of changes going on right now at the beginning, because we did add a lot of material to the model, so it's got to kind of a little bit recover and catch back up to where it was before. We'll see we've had a huge jump in the pressure drop. But as this runs out, I can maybe make these oh wait, I'm hitting the wrong thing. We can see that the pressure, kind of our flows are catching up right here. If we want to expand out that derived parts and add the new regions to it, we can easily do that right here. And one thing is we've seen, actually we should have a converged solution right now, that we've actually got, move this out of the way, kind of where we were before. We had, about 3 kilograms per second going through that outer pipe. We've actually got about 10% less going through it now with our updated mesh structure. And we got a little bit more flow going through pipe 3 than what we were originally predicting. And back through, you can see now we have clear lines going out. We're no longer getting warning messages coming up. So that's the end of this demonstration. I hope it was very fulfilling for you, and that you would come back and check stuff out from us again. Thank you.